Now let me at the end do a small example with another example on advertising, on an advertising game, and then we'll end. So in this game, so this is the fourth application on advertising. So here the game is the following. So first, player one, there are two firms, so it's advertising with two firms. So first there's firm one that decides the amount of advertising, okay, denoted by A, and then there is already firm 2 which is present in the market, and firm 2 can decide whether to stay in the market or exit. Okay, so that's a discrete decision for firm 2. Firm 2 can stay in the market or exit. Okay, if the second firm exits, then the payoff to the first firm is 1 minus A, and the payoff to the second firm is 0 due to the exit. If the second firm stays, then the first firm's payoff is A minus A squared, and the second firm's payoff is 1/4 minus A by 2. Okay, so now again we can apply backward induction here, right? We can check what would be the best thing for firm 2 to do in this node. Okay, now if firm 2 stays, then payoff is given by this, and in firm 2 exits, the payoff is 0. So firm 2 would like to stay if so firm 2 stays if quarter minus A by 2 is greater than equal to 0. Okay, let's say, which means that A is bigger than equal to, sorry, not bigger than equal to, A is smaller than half. Okay, if A is equal to half, then it's exactly 0. For all A is less than half, that expression is positive, and so firm 1 would stay. The question is, knowing this strategy, so suppose, so this is the optimal decision of firm 2. Knowing this, what would firm 1 do in the previous one? So that's the backward induction logic. Okay, so if firm 1 chooses A less than half, then firm 2 would stay, and firm 1's payoff would be A minus A squared. And if firm 1 chooses A bigger than half, then firm 1's payoff will be A by 2. Okay, so let me plot, so let me write down firm 1's payoff. So sorry, so firm 1's payoff is 1 minus A if A is bigger than half, and A minus A squared if A is less than equal to half. Okay, now given that A is less than equal to half, what is the maximum thing that what is the maximum payoff that firm 1 can generate? So what is the maximum of this given that A is less than equal to half? So suppose this constraint was not there, what would have firm 1 chosen if firm 1's payoff was this? What A maximizes this object in absence of this constraint? Okay, so let's find that out. So suppose if I maximize a minus a squared with respect to a, I get the first order condition that 1 minus 2a must equal 0, which tells me that a equals half. So we see that this expression is indeed maximized at a equal to half. Okay, so this condition is satisfied, a less than equal to half is satisfied. So at then a equals half, forms payoff is half minus a quarter, right? Half square, which is given by a quarter. So that's the maximum payoff he can get in this range. That's the maximum payoff. What is the maximum payoff for a so the question is whether this is bigger than this maximum payoff under this. So so the maximum of 1 minus a, given that a is greater than equal to half, is given by half, right? At a equal to half. So we see at a equal to half, this payoff is bigger than this payoff. Okay, so then but at a equal to half, we see that from the previous analysis, a equal to half, the payoffs are exactly identical for player 2, right? At a equal to half, this equals 0, right? From this, so when a equals half, then player 2 is indifferent between staying in and exiting, and therefore exiting is a best response. So we can have an equilibrium, a subgame perfect Nash equilibrium, where player 2 chooses to exit for a equal to half. Okay, so in which case player 1 would like to choose a equal to half, in which case his payoff will be half, right, which would be bigger than the maximum payoff he can get in a less than half range. Okay, again notice that here I am assuming that player 2 must choose exit when the player 2 would choose exit when player 2 is indifferent between exiting and staying in, right? Because if player 2 chooses to stay at a equal to half, the problem is that again here at a equal to half, his payoff is 1/4, but for a slightly bigger than half, the payoff jumps to 1 minus a, which is something close to half, okay, rather than a quarter. So then again we run into the problem that player 1 doesn't have a best response. For every a which is slightly closer to half, and even more closer to half, but still above half, we'll still get the case that the player firm 1 will get a higher payoff. So that's why we'll not get a best response from firm 1 when player 2 strategy is to stay in when player 2 is indifferent. Okay, so this gives us then a subgame perfect Nash equilibrium of the game. So the subgame perfect Nash equilibrium of the game is given by player 1 chooses strategy a equals half. That's the strategy of player 1. What is the strategy of player 2? Remember, strategy is to specify an action for all possible nodes in which the player can move. So for each a, player 2 has to make a choice whether to stay in or exit, and so player 2 strategy will be a function of a. So player 2 strategy is a function of a, is to exit if a is bigger than equal to half, this equal to is important, and to stay if a is strictly less than half. Okay, so that would be the strategy. Because if player 2 strategy is to stay if a is less than equal to half, then we don't have a best response, right? So so this is the game. So let me stop here. So this sort of gives you an idea of how to apply subgame perfect Nash equilibrium in various kinds of scenarios, game theoretic or strategic scenarios that involves sequential move by the players. We will discuss some of these in the next class as well, and then move to some new topics. Okay, thank you. Goodbye.